Hello everyone, welcome to Tech Talk number 47. Today's Tech Talk is high performance voltage regulation with distribution STATCOMs, distribution class STATCOMs. Today with us we have David Oteman from American Superconductor. But before we start, let me remind you, PDH contact certificates, the contact hours that you will receive or can receive after this presentation can be obtained by sending an email to myself or to Matt Marcette. Please send it only to one of us, not to both of us. So David Oteman is with American Superconductor. For those who do not know, that is our mother company. We were purchased by American Superconductor on October 1st, 2020. We first met Dave on Tech Talk session number 25, where we met the D-VAR VVO STATCOM system up close. And during that presentation, he discussed how the STATCOM could be used for motor starting and what this VVO STATCOM is. Remember, one of the key things about STATCOMs is they're fast and precise. And I kind of have a little symbol here, fast and precise. And capacitor banks, which is what NEPSI produces, is more of a slow and not so precise device. So Dave is with us today, and he will be discussing the VVO STATCOM system and how the distribution STATCOM system works on distribution systems. Hey Dave, how you doing?
Hey Paul, good. Thanks for having me again on the Tech Talk series.
Oh, that's great. So Dave, maybe just introduce yourself again, what you do at AMSC before we get going with the presentation, and then you can turn on the presentation.
Sure. Yeah, so I'm currently the product line manager for our distribution class STATCOM product line, which we brand name D-VAR VVO. My background is in research and development engineering, so I've spent most of my career designing products for power system automation, as well as for power electronic applications for renewable energy, wind and solar included.
Okay, great. Well, I'm glad to have you back here, and this VVO STATCOM solution seems to be a very pertinent solution. Just last week we were talking about hydrogen, and during that Tech Talk, one of the participants in the Tech Talk talked about the requirement for the electrolysers, the devices producing the hydrogen, that their voltage is critical for their operation, and it's actually pertinent today because the VVO serves that function. It helps to regulate voltage, and this whole green hydrogen concept and using renewable energy to develop hydrogen through electrolysis, it requiring precise voltage. The VVO is that device that can do that. So we're happy to be talking about that today. So yeah, so Dave, you might as well get going with the presentation, and I'm going to pepper in some questions, and I do want to remind the audience to please ask questions in the chat box. Dave will be answering those questions at the end of the presentation today, though. So just please ask the questions as we move along, and then we will address all those questions at the end.
Great.
All right.
Well, thanks for joining in today. So the topic for today, we're going to share applications of distribution class STATCOMs specifically for voltage regulation in distribution systems. I thought it was good to go through a little context here before we work into the applications a little more for the STATCOM. So what this slide is showing is a timeline of voltage technologies and power factor correction technologies on the distribution grid. And what we can see is basically in the early days of electrification, as really society started to really use electricity more broadly, larger power plants were being built, and then the need to distribute that AC power along further distances became necessary. That's really what drove those longer distances, is really what drove the need for utilities to own line regulation equipment to compensate for that voltage drop along those longer lines. And then in the United States, there was a period of rural electrification where that problem really even kind of expanded even further. So very long feeders across a lot of the United States, in the Midwest and West, up through the 40s and 50s. In the 50s and 60s, there was a proliferation of air conditioning. Air conditioners are motor-based loads that consume a lot of VARs. For utilities to be able to operate their system efficiently and not have to source those VARs all the way from generators, it became very economical and prudent to put in some VAR compensation near the loads that were consuming those VARs. So that's where we see a large proliferation in specifically switched capacitor banks that utilities don't. So these are the banks that you'll see up on a utility pole, for example. Fast forward into the 1990s and 2000s. So the utility system now has a combination of step voltage regulators as well as switched cap banks installed, thousands of devices on most larger utility systems. Then this really became kind of the era of efficiency, and not just in volt VAR control, but kind of across the board, more efficient appliances, more efficient lighting. Obviously, LEDs started to come of age towards the second half of this. And basically, from a voltage and power factor correction standpoint, this was the first time when utilities really started to take control of these assets from a centralized control standpoint. So previously having those local controllers just turning on and off these devices, or tapping these devices based on local knowledge. Now with the advent of fast communications and reliable wireless communications, utilities were able to take it to the next notch of being able to really control now large arrays or fleets of devices. And the big benefit there was really being able to reduce peak demand. That's one. You reduce peak demand, you really get to defer a large transmission investment, for example. And then also efficiency. So we can get our kilowatt hours required down by running the voltages more flat and more optimally across large portions of the distribution system. And we still see these deployments growing today. So there's still feeders today that are going towards this software automation of these capacitor banks and line regulators. The key point is, if we look back from today, all of these technologies have really been designed around managing at the average voltage on the system. So let's think of taking the voltage in 15-minute intervals. Today's voltage regulation system is really good at managing that voltage on an average basis. What today's system is not able to do well at this point yet is really what's happening in between those 15-minute intervals. And why that's becoming relevant now is really because we're in the age of distributed generation. So distributed generation is driving increased variability onto the distribution system. Higher throughput manufacturing, Industry 4.0, is also driving more demand on our distribution systems. And the utility industry really has an opportunity now to move beyond average voltage control, average power factor control, and dynamically control, or this is what we call power quality, move to controlling both the average voltage as well as the power quality. So that I showed the name D-VAR VVO on that first slide. So D-VAR VVO is a product that we developed at American Superconductor. It's specifically because we saw this trend of distributed generation happening. STATCOMs are actually not new to the power system. They are actually currently used very extensively in transmission systems. Transmission systems use them to integrate renewables, and also use as a primary voltage regulating device on the transmission system, especially in longer areas or weaker areas of transmission. So the transmission system is actually mostly a shunt regulated power system. A STATCOM is a power electronics inverter that only processes reactive power. So unlike the inverters that some might be familiar with, for example, a solar inverter or a wind inverter or a battery inverter, which processes real power and maybe a little bit of reactive power, The unique thing about a STATCOM to understand is that it's only processing reactive power. It's actually only capable of processing reactive power. And then it actually turns out that fortunately, because it's only processing that reactive power, there are some nice tricks from a technology standpoint that we were able to make in the development of our D-VAR VVO, a STATCOM, and specifically some nice tricks to make it very power dense and very compact. STATCOMs can be used really for 3 different purposes, either controlling power factor or VARs directly in the feeder. And then the bigger focus of today's talk is actually going to be how do we use these STATCOMs to control voltage. So those VARs that can be absorbed or supplied dynamically by a STATCOM then can directly be used to directly regulate voltage as well. What are some advantages of STATCOMs now specifically in the distribution system? So I mentioned they're already being used quite extensively in transmission. Why does it make sense to bring this technology into the distribution system? This is showing a representative feeder that would be experiencing a large amount of, in this case, what's shown is variable generation. So this distributed generation that is coming on to the power system is primarily solar and in addition, wind. In either case, that generation is characterized by variability. As the clouds come by, obviously that's going to cause power fluctuations. As the wind varies, the same thing. For the case of solar, we know that solar plants or solar feeders with a lot of solar can experience upwards of 50 cloud pass events in a single day. So that's really something that the distribution system was not built out to support. And the traditional technologies that are managing average voltage were not built out to support that. So I'm just showing a little summary quickly here. So switch caps, typically switching 4 to 6 times a day in order to actually prevent power quality problems. So when a switch cap switches, it actually causes a step change in voltage. So most utilities limit their operation just for that reason alone. In addition, the mechanical switch will wear out if they operate too much. So most utilities are in that 4 to 6 operations per day limit. And then of course a capacitor bank cannot pull the voltage down, it can only boost the voltage up. When we have generation causing reverse power flow, we actually need to pull the voltage down, so the cap bank's not going to help us there. Line regulators really are also quite limited in terms of their operation. So if we're trying to compensate for over 50 events a day and both the ramping up and down of that, line regulators are also not adequate to solve that problem, and they're not reliable enough to solve that problem. And we'll talk a little more about that. So a power electronics device really addresses this gap that we see in the existing line regulation equipment that utilities use. And that's what's shown in the middle of this graph here. So power electronics device is going to be able to continuously control. So thousands of times a second, these power electronics are able to sense and react to the voltage changes or the VAR changes continuously. No practical limit on operations. So as we get these larger fluctuations, whether they're driven by solar, whether they're driven by high throughput industrials, power electronics is not sensitive to that. That's a big advantage why our customers like our solution. They don't have to think about, oh man, is this going to wear out more quickly because now this circuit has variable load on it. And then finally, the ability to handle power flow in either direction is an inherent property of a STATCOM. So it just does not care if power is going forward, reverse, or if it's very rapidly going back and forth between forward and reverse. The controls are inherently robust to that, and it's just one control mode. You don't have to, tell it and make it aware that, the power might be changing direction, for example. So other nice advantages that our utility customers like about this technology. And at the end of the day, we're able to now fill that gap where we can control power quality on a continuous basis and not have to be concerned about whether that'll wear out the equipment or not. I mentioned the limitations on tapping for a line regulator. So that's driven by very real failure modes. So as we see more solar feeders with very high adoptions of solar, this is becoming a serious problem also for line load tap changers. Here's actually a summary of all the mechanical failure modes in a tap changing regulator. So I've got 10 listed here. One of them actually has 8 separate components that can fail the same way. So there's actually 17 failure modes in a line regulator, and that's just a single phase regulator. Now we go to a 3-phase bank, multiply that by 3, there's actually 51 mechanical failure modes in a line regulation system. Every single one of them will be accelerated with additional operations on the equipment. So this equipment is not a match made in heaven for more variable generation, and it's one of the things utilities need to address now moving forward. As I mentioned, the power electronics advantage now, we have literally no moving parts in our D-VAR VVO solution. So it's literally 100% solid state power electronics, no mechanical failure modes to deal with.
So
We like to.
So Dave, let me just summarize. So cap banks are mechanically switched, and we've talked about mechanical switching before. Capacitor banks, typically 10,000 operations is what a vacuum switch is rated for. So if you just kind of do a simple calculation, if you're doing four switching operations a day, that's 2,500 days worth of operations. So maybe 6 years max so that you might get out of that switching device. And with the PV systems, is this concept of distributed generation, which is becoming really a major push in industry to go carbon free, right? So PV is being pushed, rooftop solar. You have distribution feeders, which can be very long, being pushed up and down in voltage based upon really the sun, if the sun's hitting the array or not. So those switching operations could quickly wear out a capacitor bank if they were to set the control such that it was constantly controlling based on voltage. And the same holds true for the voltage regulators. Same exact concept that you can only have a limited number of switching operations.
Yep, and a line regulator will typically have more than a cap bank, but not to the extent where it addresses this limitation sufficiently.
Yeah. So interesting. There's no limitation on the number of times this VVO switches, correct?
There is not, and that's when we are having this application, the asset managers at utilities love the fact that they can say, well, it doesn't, whether I'm on this circuit or that circuit, the lifetime is basically constant. Asset planners plan on 20-year lifetime from the D-VAR VVO STATCOM. As opposed to, you might get 25 years of life on a slow circuit with a line regulator, but then on a high renewable circuit, you might get 2 years. We have customers coming to us with 2.5-year failure modes on their line regulation exactly for that reason. So having to be able to think about your lifetime depends on where it is in the system is not a comfortable position for a utility to be in.
And it's only going to increase from here because of the push for renewable power, right? So
yeah, exactly. Yeah. Yep.
Okay. Well, very interesting.
Thanks for the question, Paul. We like to kind of create a framework for power quality on the distribution system, and that's what I'm sharing in this slide. So we break it down into 8 different, really, I guess, technical problems, you could say. We went over basically that regulated, unregulated voltage and low power factor. Those are pretty well addressed today by the power factor correction caps and the line regulators. That's the average voltage being managed. But as we can see, there's basically 6 other issues that really are not well addressed today at all. And a STATCOM is ideally suited to address these other issues, in addition to the existing voltage and VAR management. So just briefly, let's swing through these. So load rejection over voltage. That is a common problem on longer feeders where you lose a load suddenly, and that can happen for a lot of reasons. A recloser opens, a large customer has an issue and trips their breaker, and very common issue towards the end of a feeder where the voltage can spike up to 20%, 25%. A STATCOM on the end of a feeder can pull that voltage right down and actually prevent it from happening in the first place. Flicker, a lot of causes of flicker, anything in the realm of crushing operations. We see electric industrial heating that is based on electric heating is very commonly causing flicker. Arc welding and arc furnaces cause flicker on the distribution system. A STATCOM is in fact fast enough to compensate for flicker and bring those feeders that have those kinds of load on them, it's able to bring that into compliance for not just the industrial, but all the other customers. Rapid voltage changes are commonly caused by motor starting events. Big, large inrush, we did a tech talk on that. STATCOM's fast enough to compensate that. Voltage rise, because it can go inductive, it can pull down voltage rise especially due to DG. When you have a low, lightly loaded feeder with a lot of DG, it's all about bringing the voltage down actually. And STATCOM's ideal for that. And then a couple more is STATCOM can filter harmonics actively. So STATCOM is not a dedicated active harmonic filter. However, when it's installed on a feeder, it can be used additionally to filter the 3rd, 5th, and 7th harmonics. And then lastly, unbalanced voltage. So the VVO distribution class STATCOM is able to independently operate all its phases. So for example, phase A could be fully inductive, phase B could be fully capacitive, depending on how unbalanced that system is. And a STATCOM is generally a more effective way to compensate for voltage unbalance than either a cap bank or a line regulator is. So we see that we can cover really what I call the gamut of power quality issues based on this power electronics technology, and really fill that gap that today is not being met well with existing mechanical equipment.
Yeah. Hey, Dave, I might add, so this number 1, I almost consider distributed generation to fall into that slot 1 too, because as the solar array power output goes up and down, it's more or less a load rejection phenomenon going on there. It's a drop of real power up and down. So in a sense, a load rejection phenomenon going on. The other thing is for number 7 for capacitors. Number 7 in relation to harmonics there. Capacitor banks cause resonance, and this VVO system is not a capacitor bank. It doesn't have a capacitive reactance, and therefore it doesn't contribute to a concern for resonance like a capacitor bank does. So we talked about in other tech talks, we've talked about this phenomenon of resonance, and even in environments where the harmonic currents are real low, when you have resonance, you typically have a voltage distortion problem. So another benefit of this VVO product is it's less likely to cause resonance, which is less likely to result in, therefore, high voltage distortion, which is a major power quality concern. And
that's accurate. Yep. And the STATCOM actually does not look like an impedance. So we'll talk more about that in the application section too.
Okay.
Here's a waveform on a feeder that's highly saturated with solar, just to kind of show some intuition as to these power quality problems. So I showed the 8 power quality problems. This has a bunch of them on it. What's shown on the left is this feeder prior to mitigating these voltage issues, and this feeder data is shown during a spring day where there is significant net reverse power flow on that feeder due to the solar generation. And it's also a partly cloudy day. So we can see before the clouds come in the morning, there's not so much of an issue. Here's where now that solar resource is fluctuating by megawatts on this feeder and driving these voltage violations. And we can clearly see the high voltage at full output, as well as when there's sudden dropouts due to the cloud pass, rapid voltage changes that are considered violations as well. Very, very real problem when it's gone and mitigated. This was about 7.5, 8 miles down on a radial feeder that this data was taken. And on the right is that same, so different day, but basically partly cloudy day, same feeder, same problem. After running the STATCOM at near that very same location. And we can see that just adding a STATCOM alone, no other changes to the circuit, so that the existing mechanical equipment didn't have to change, the settings didn't have to change, it was just put in a STATCOM and walk away from the problem. And this completely addressed all those power quality issues. I talked about distribution class equipment, and we know that historically transmission systems is where STATCOMs really got their start, and they're very mature and widely adopted. So bringing this technology into the distribution system actually requires a product that's engineered from the ground up to meet distribution requirements. So it's not like you can take a transmission STATCOM and maybe just take part of it and start using it. It really has to be re-engineered, and that's what we did with the D-VAR VVO product line. And what can be seen here are a couple of examples of installations. So the 15 kV class installations on the left. So that's a 1 MVAR STATCOM installed directly in the existing right-of-way. So one of the big advantages of this technology is, just like utilities use other overhead equipment in their existing right-of-ways, like a transformer, like a bank of line regulators, D-VAR VVO can be installed in those same existing right-of-ways. We show a 25 kV installation on the right picture, and with a 25 kV installation, that same H-pull structure at 15 kV is used, and then basically there's a step-up transformer required. That's the green apparatus on the ground there to convert the 25 kV overhead to a little 15 kV substructure here. So in this case, the installation also fits 100% within the existing easement that the utility has access to. So in either case, we're able to stay within those existing right-of-ways, which is critically important, so that utility doesn't have to go off and try to acquire more land, for example, which can be very expensive and time-consuming. We do have nameplate configurations from 1 to 4 MVARs. We're showing the 1 MVAR there. We also do have a metal enclosed option. So Paul and I will be doing a tech talk at some point in the future on that. So we're showing our overhead solution in these pictures. We do also offer a metal enclosed version of that. Just to clarify on these single lines down here, so we're able to direct connect up to 15 kV, and then above 15 kV, it's still fully distribution class, but we do require that pad mounted transformer with that riser pole next to it to make that happen in the overhead installation.
So Dave, is it worth saying that maybe this is a good drop-in replacement for places where you have these voltage regulators? It's the same elevating structure. Is that a fair possibility?
It is a fair possibility, and we'll show a little bit later in this tech talk how to think about that. So basically, the short answer is, for upstream regulators that are closer to the substation, say within the first protection zone, typically those need to remain installed. But where the STATCOM really shines and really brings all the advantages that we covered is on the downline portions of a feeder. So 7, 8 miles or longer down line. Some feeders are 20 miles. Anywhere along those downline portions is where it is actually possible to replace the line regulator altogether, and then you get all the benefits that we covered when doing so.
So Dave, I'll mention this metal closed option just for a moment. We're building our first, I would say, prototype unit now in the shop here, and you didn't mention the future for pad mount, but there, of course, would be a future for that pad mount option too. That will be down the road, right? we can talk about maybe in the future. So.
Absolutely, yes. And we have several of our existing customers that we're looking to do a pilot with in that pad-mounted version. So to distinct what Paul's talking about is, we show the overhead pictures here. The metal enclosed is specifically designed to go at a facility. So, for example, an industrial customer would typically accommodate that. And then the pad mount would then be most likely owned and operated by a utility for example, underground systems that are longer, or any time you really need that pad mounted apparatus as opposed to this overhead apparatus.
Yeah, URD, right? URD type systems and things like that, right?
Yep.
Maybe you want to comment just a moment about 15 kV, why you went with 15 kV versus 25 kV.
Yep. Yeah, so that's a great question. So basically, around 80% of the distribution infrastructure in North America is still 15 kV class. So that really kind of hits the sweet spot of the market need. And we were able to do that most cost effectively. And then, that step-up transformer, most utilities already use that step-up transformer elsewhere in their system. So it's familiar, it's easy for them to buy, and not such an expensive component at all, very reliable. So that was kind of the right choice. For sure, as 25 kV distribution grows, we'd like to replicate the 15 kV version at 25 kV. That's down the road a bit as well. So
it's 1247, 13.2, 13.8 kV type distribution systems.
Exactly.
Primarily. And 4-wire multi-grounded neutral, is that the other requirement?
Yep.
Or, yeah.
So the VVO can be floating Y. The installations that are shown in this picture are actually grounded Y installations. We also have installations that are floating Y, especially for 3-wire systems. So a lot of Europe, a lot of the UK is 3-wire, Australia. So either floating or grounded Y are supported.
Okay.
And then I should mention as well, single phase. So we do have installations on single phase laterals. If you have a long single phase lateral, for example, with a lot of rooftop solar coming in on it, this can be a really nice way to just manage the voltage on that long lateral, for example.
Yeah, and help balance up the voltage back at the connection point onto the main feeder, right? It's to help maintain that voltage at that location.
It does. Yep, exactly. And that's right. So the single phase, and in all of these installations, each phase is able to operate independently. So, for example, phase A can be fully inductive, while phase B is fully capacitive if that were required to balance the voltage. And the system can also operate only in a positive sequence mode if that's desired. So we can, by default, we're in that independent mode. But if it's desirable, actually for motor starting, it's often appropriate to just be in that positive sequence mode. Then in our SCADA settings, all you have to do is say, nope, just go straight positive sequence, and we won't do the unbalanced thing.
Okay.
Yeah, great questions, Paul. So we saw the actual installations. Just briefly, what I want to point out on this slide is really the no routine maintenance achievement that we've been able to accomplish with this solution. So you'll notice that there's radiators on each of these power electronic units. The principle of operation of cooling is actually quite similar to that used in a modern distribution transformer. So there are literally no moving parts. There's no fans, there's no pumps, and then of course, there's no air filters to change out then. There's no, coolant fluid that's got to be managed or something like that in a forced cooling system. So it is all based on immersion cooling, just like a transformer will naturally circulate and cool off the transformer. And the same sealing system that's used in transformers is also used here. So these are IP65 rated units, and you won't have the problem of ingress that you can run into with air-cooled equipment either. So it's really these design attributes that make it a distribution class. So I mentioned what's the difference between transmission and distribution. Getting to the point where there's literally no routine maintenance, where there's literally no mechanical failure modes, is key to getting this so that it's practical for utilities to be able to install it and know that it's not going to wear out faster on one feeder than the other because of the no moving parts and no routine maintenance. To recap the technology portion here, so what is a distribution class STATCOM, and what are the technology advancements now that this distribution class STATCOM is bringing to the table? So number one is control of power quality. So as I mentioned from previously, utilities have done a good job of managing average voltage. They have not done a good job, and frankly haven't had the tools to do the job of managing power quality. That's different now. That's all changed moving forward. Near constant life characteristic. To re-emphasize again, power electronics don't care how many times they cycle up and down practically. So you know, any kind of practical load on a distribution system, no matter how much it's fluctuating, it's not going to cause an early wear out of a power electronics device. Power electronics device does wear out eventually, okay, but that mechanism has nothing to do with how many times it's fluctuating its output. Big advantage that utilities love, because if they have an O&M, a premature asset wear out, the utility ends up eating that cost, especially if it's happening, you know, it's kind of systemically across their system. Inherent safety, I didn't hit on this really until now, but this is another real advantage. So number one, the shunt connection is very safe. You talk to a line person, you talk to a line crew supervisor, they are going to tell you, no, hands down, installing a shunt STATCOM, way safer, way more secure, way less risk than a line regulator in series. One of the worst failure modes that can happen to a line crew is a bypass failure in a line regulator. Very dangerous. Line crews are nervous about it all the time. This completely avoids that issue. And then there's a lot of, obviously a lot of prudent activity around energy storage today. And energy storage is definitely a great, important technology for our energy transition. But one of the things to point out here is that we're able to deliver all these dynamic benefits to the voltage and the power delivery system without the use of batteries. So we like energy storage. However, we know it's got a problem around safety. It really needs to be managed. And it can be managed, but then that adds expense. So the VVO, to be clear, does not use any batteries whatsoever in the design. Zero routine maintenance we hit on, and then distribution class power electronics. So very high density power electronics. I mentioned the STATCOM allowing us to play some tricks in power density. That's how we were able to get this to be pole mounted. That's how we're able to get it to be pad mounted. And our metal enclosed version, which we'll share in the tech talk, very compact. And that allows our customers to fit it within their existing easements and thereby avoid having very expensive land acquisition requirements. So that kind of recaps the first part of the tech talk here, where we really wanted to underscore, okay, what does it mean to be a distribution class STATCOM? And now what, you know, really from a utility perspective in particular, what do these benefits look like from a technology perspective? So I'll run through some of the key applications now. Basically, there are three major applications that I'll share. One of them we've mentioned, it's called accelerating renewables. So a lot of utilities are now starting to put out standards for themselves to get to 100% renewables. So previously it was kind of at the state level setting RPS goals. We now see states announcing plans to go 100% as well as utilities. So getting to 100% renewables, if you look underneath the hood of that, most utilities resource plans absolutely include distributed generation in that. Distributed generation, one of the nice things about it is that the distribution system, the wires are there already. They're currently using load, but to get generation on, you have the infrastructure there if you can find the spots to connect. So that's one of the main reasons why we see distributed generation continuing to come onto the system. We saw, I think it was 6 gigawatts last year come onto the United States system. That's a good amount of generation, and we see that continuing to grow. So one of the differences of connecting variable generation in a distribution system as opposed to transmission is that really two main differences. So number one, you got customers in your distribution system. So those voltage waveforms we looked at, those high voltage violations, the misoperation of mechanical equipment is going to potentially impact existing customers. So when utilities look at permitting large generators or rooftop solar to come on the system, they have to be concerned with protecting the power quality of their existing customers. So that's number one. Number two, utilities also have to be sure to protect their own assets. So we talked about this variability. We showed very clearly how existing mechanical assets lifetime is directly sensitive to that variability. So utilities have to be sure that they're protecting their assets, not wearing them out prematurely as part of these interconnects as well. So, and that's really where the STATCOM technology is able to address both sides. So we're able to protect existing customers from those power quality issues, high voltages, aggravating voltage fluctuations, and we're able to protect tapping equipment like load tap changers, line regulators from excessive overoperation. And so what I'm showing here is actually on the utility system where the utility would own the STATCOM in this case. And it's also possible to have STATCOMs at the solar plant. It turns out there's a lot of advantages to having the STATCOM located on the main feeder, including making sure that all the existing customers are having excellent power quality and protected against not just this solar plant, but potentially future solar plants coming along on that system. Whereas if you have the STATCOM kind of behind the fence at the solar plant, those benefits of really protecting existing customers, protecting existing utility assets are harder to achieve. So one last comment here. Utilities have historically offered wire-based upgrades. So one of the techniques is known as a dedicated feeder or express feeder. And that allows the utility to protect these customers from power quality issues. However, it's very expensive, very time consuming. Basically, the VVO is able to achieve better power quality than a dedicated, specifically when there's voltage violations, and at a small fraction of the cost because it's just an apparatus. And I should mention we're going to do a deep dive tech talk on just this application. So I just wanted to share it as one of the key applications for distribution class STATCOMs today. But we're not going to deep dive this. There's a lot of deep content that we can go into here. So please keep that on your radar, especially if you're dealing with some of these problems. Second application that we'll cover today is what we call unserved energy due to power quality issues. A lot of utilities serve industrial load, and it's not uncommon for industrial load to create large fluctuating power profiles. So crushers, shredders, resistive heating, as I mentioned previously, these are some loads that can really drive significant variability onto feeders as well. And what happens in this scenario is there's always three people involved. So there's the utility, of course, the industrial customer causing the flicker problem, for example, or power quality problem. And then there's other customers. And because on the distribution system, there's pretty much always other customers. So very quickly, there's three people involved when these power quality issues occur. And it becomes often pressing, and often there's a finger pointing game happen. So common types of problems, as I mentioned, flicker. The conventional way that this has also had to be addressed when these problems pop up, line regulators, cap banks aren't fast enough. So the utilities have historically had to go to the wire-based toolbox. The VVO is also able to directly address these types of power quality issues and can be an apparatus-based solution at a much lower cost, much faster, and address these issues and basically allow that industrial to get back online, allow the utility to now serve that customer again, because anytime a customer is causing a power quality problem, they often have to curtail or even stop that process until it's fixed. And then, of course, the other customers are then able to be served back with a high service quality again. So another good application for the technology. And also the common theme here is just back to our initial 8 problems that we covered, and the 6 that cannot be addressed today, whereas the VVO can address these very dynamic problems. Last application that I'll go over is serving downline loads, especially on longer feeders. So the power system and the distribution system in particular, the longer the feeder and the further down line on that feeder a customer is or a load center is, the harder it is to serve from a voltage standpoint. And we see utilities run into constraints, voltage constraints, that prevent them from actually being able to serve additional load. So on the bottom graph here is actually a graph of a long feeder profile using line regulators. And this was a utility that we were working with that was looking to serve an additional 1.5 megawatts of load. And we can see some of the challenges that pop up when that happens. So specifically, very discontinuous voltage profiles due to the line regulators. And other common issues include, for example, load rejections, which I covered. When a sudden load were to drop, all of those voltage regulators are ramped up. And right after that load trips off, you can get very high voltages, which can prevent the ability to serve these load growth towards the end of the feeder. Other problems is during reconfiguration. So utilities build their system to be backed up by other feeders. And when that system has to get backed up, series regulators are not the ideal way to be able to accommodate that power flow coming in a reverse direction now. So STATCOMs can actually be used as the primary voltage regulator on these longer downline locations. So we're showing Reg 3, Reg 4 here. On this circuit, the VVO actually is able to replace those 2 downline regulators and be the primary voltage regulator and address these voltage constrained issues that a typical series regulating device is not going to be able to address. So here's a case where it's very conventional. The utility wants to serve additional load, and just a customer wants to expand a plant, for example, or expand for some reason. And here's a tool now that can let us very quickly install and use an apparatus-based approach to serving this additional load. Additional loads in the 1.5 to 2.5 megawatt range are pretty achievable when a voltage constraint is there. So at some point, obviously, if a load of like 5 megawatts, for example, is needed, at some point it doesn't become it's not a voltage issue anymore, it's a thermal issue. And at that point it would be appropriate to, for example, reconductor or run a new feeder. But when it's only being constrained due to voltage, that's where the STATCOM is also a really nice tool for being able to serve this load. So that brings us through the main applications that I wanted to share today. Paul mentioned mentioned about how does a STATCOM operate as a voltage regulator. So we've been talking about that, and it's a different principle of operation than series voltage regulation. So here now, briefly, I want to run through the key concepts of how a STATCOM, especially a downline portion of a feeder, is able to act as that primary voltage regulator. So here's a graph that is a convenient tool to see how much impact a shunt, in this case VVO STATCOM, can have when installed on a power system. You just need to know two parameters. Number one, the fault power, and that's along the x-axis, and then the x over r ratio. Both of those power system parameters are well known. The utility knows them. Most large facilities have that data readily available too. And with those two parameters that are readily available, it can be determined how much voltage regulation ability a VVO STATCOM has. So let's take an example. 30 MVA fault power, which might be pretty common about 7-8 miles down a feeder. And then very common conductor sizes, X over R's, are in this range at 1.5 to 3. And so there on that portion of the feeder, the STATCOM can buck or boost by plus minus 3%. If we go to a more common long feeder example, so let's say 10 miles, more than 10 miles out, we're more commonly now going to be on the left portion of this graph. And we can see one VVO STATCOM can buck and boost by plus minus 5% on those longer locations. Same graph, same concept, and what we call now our hybrid configuration. So a very nice cost-effective way to improve the voltage impact capacity of the VVO for specifically boosting the voltage is what we call a hybrid. So we pair up the VVO, which is plus minus 1 mVAR, with a fixed 600 kVAR cap bank, and the controls automatically support that configuration, and that gives us basically another 50% of voltage impact. So we take that same 30 MVA case. Now we're running at the ability to boost by 5%. So this is very handy for load serving applications in particular. And then that same now longer feeder downline, we're now being able to boost easily in the 8% range. So hybrids are a very cost-effective way to be able to provide more impact from a single STATCOM installation. So these graphs are basically showing how much impact we have at a single point at the of installation. So this is specifically where the STATCOM would be installed on the feeder at that one point. It's important to understand how the voltages along the feeder are being impacted by a STATCOM in a voltage regulation application. And that's what's now being shown on the next couple slides here. So what is shown here is a representative feeder that's 14 miles long that has the load spread out along that feeder. And just for clarity purposes, we've actually stripped out all the voltage regulating devices. So what we're seeing here is a profile just due to the load on that feeder. And what now we're going to show is how does a STATCOM impact this voltage profile? So not just one point of voltage, but the total profile of the feeder as we put it at different locations on that feeder. So here's the first graph of that, where we're putting a STATCOM 2 miles from that substation. And now we're going to keep moving that STATCOM 2 miles, another 2 miles out each time. So now we're 4 miles from the substation, 6, 8, 10. And what we can see is that the further out the STATCOM goes, the more impact it's able to have on the voltage. And so that's what I described previously, where the downline locations on a feeder are where the STATCOM is most effective, which is good because the downline locations on a feeder are the ones that are often most challenged by these power quality issues. So let's just finish this out, and we see that now at the very end, we're in fact impacting voltage by about 8%. The same concept we can now look at in the context of now reconductoring a feeder. So we're going to go through that same idea now with basically 2 miles of reconductoring from a 1-aught conductor to an ACSR 477. And here's that same profile, baseline. Now we're going to reconduct the first 2 miles and keep reconductoring another 2 miles as we go out. And the striking thing about reconductoring from a voltage standpoint is that it has a very similar impact as the VVO. So reconductoring also provides thermal capacity, of course, but when it comes to just being able to improve voltage, the impacts are quite similar. And this is why we sometimes say that the VVO has the effect of stiffening the circuit, exactly for this reason. And then this is why when I went through the applications, we're able to use the VVO in lieu of reconductoring as a tool. From a voltage standpoint, when the problem is voltage only or power quality, the VVO becomes now a much lower cost solution, much faster, much easier to install solution than having to rewire a lot of a circuit. And then just briefly, this is that same profile now if we both reconduct to the feeder and use a STATCOM on that feeder. And as we can see, the STATCOM still is very effective at boosting the voltage on the feeder because it's working primarily with the inductance of that feeder. So to recap, the principle of operation for voltage regulation on a distribution system, what we just reviewed. So the D-VAR VVO, number one, continuously and precisely controls the voltage using VARs. So shunt device, not a series device, using VARs to regulate that voltage. You need fault power and X over R, and that's all you need to be able to determine how much impact the VVO will have, depending on where it's installed in the system. The VVO automatically bucks or boosts voltage as necessary, so that's one control mode. It doesn't have to be told to buck or told to boost separate. It just needs a voltage set point, and it's going to automatically do the right thing on the feeder, also regardless of power flow direction. And then, as we showed with those plots, this is key point. So as opposed to a series device, which only impacts voltage downstream of the point of interconnect, the VVO, being a shunt device, impacts both voltage upstream and downstream. And that results in those very nice smooth profiles. So we don't have the discontinuities that we get with series regulation, and we get nice flat voltage profiles, which are more efficient and have much better power quality. And then lastly, this idea of, okay, where is it most effective? So basically 8 miles down line and further is where we see a lot of our installations. That's because it's starting to impact the voltage by about 4 or 5% or more, and with the hybrid, even more than that. So that's really where the STATCOM is most cost effective. And like I mentioned, that's kind of a nice fit because that's where most of the power quality problems reside, around that kind of the end of that circuit on a distribution system. So that kind of recaps the key concepts of how a shunt STATCOM D-VAR VVO device is regulating voltage on a distribution feeder. And with that, we're going to just, I'll share a case study here where we're actually using the D-VAR VVO device on a longer feeder to enable a solar plant to be able to be connected. Here's a study showing this connection in the SIME software. So we have a solar plant coming in approximately 13 miles away from the substation. So here's the substation, here's the overhead feeder, and on this branch circuit is a solar plant that is 1.8 megawatts. There's a couple of voltage regulators on the circuit existing. And what this is showing is that these light green areas are over voltages on the circuit due to that solar being at full output at the same time that it's lightly loaded, so like a spring condition. On the right is a load flow in SIME showing that the VVO totally eliminates that over voltage. So you see the light greens are totally addressed there. This is a picture now of the installation on that feeder. So this was actually a 25 kV feeder where we did have to use that step up. And again, we kept the whole thing within the existing right of way. which is an important to be able to be a quick, fast solution. This is showing data that was now pulled out of our high-speed data capture and our trending module that shows the reverse power flow measured at the point that that VVO was installed, and then the voltage on that feeder being managed. So without the VVO on that feeder, this voltage was getting up to about 1.07 per unit there. So that was causing both a high voltage violation without the VVO, as well as excessive voltage changes due to the solar on partly cloudy days. So this is showing a sunny day, so we're not seeing a lot of variability, but just for clarity, so we can see how that voltage is being nicely kept within band. Here's some data that was taken during a partly cloudy day now, and what we're seeing here is the tracking performance of the STATCOM device. So this is configured in a VAR mode, and on that feeder, it's primarily acting in the inductive range, and that's not surprising because we're trying to pull down the voltage. As that solar is trying to push it up, we use the inductive capacity to pull it down, and then as the clouds pass, what's happening here is that would very rapidly ramp up and down this curve as those variabilities are occurring. And on the left, we see a histogram of the VVO. This is also on a couple of days where the loading was a little more significant. So the high voltages when the D-VAR is off aren't as high. And the utility didn't want us doing this testing on the worst case days so that we could not create voltage violations. So basically the red histogram is with the VVO turned off, and we see a wide spread of voltage as well as significant high voltage. And when the VVO is turned on, we see a nice tight histogram. And even as the solar increases on that circuit and the load decreases, so the red would be wider, that blue histogram stays nice and tight even at higher reverse power flow levels. So just kind of a good way to see how precisely the VVO is able to regulate voltage as the primary voltage regulator on the branch circuit where that solar plant was integrated. From a value standpoint, we like to use this framework here where these are kind of the different areas where we're able to make improvements, economic improvements, by using the STATCOM as opposed to alternative approaches. So the first is the STATCOM here was able to add more than 2 megawatts of hosting capacity. So the plant was 1.8 megawatts. It turns out they can now add even more solar in the future. So that was another consideration on this project. And that was achievable with existing wires. And they didn't have to make any other changes to their operating system, no other changes to upstream devices, just adding the STATCOM got them about 3 megawatts of additional capacity, and specifically eliminated those problems for that solar plant. It also reduced the operating load on the upstream regulator from the standpoint of tapping operations. So because the VVO is the primary voltage regulator on that portion of the circuit, it is very rapidly and precisely regulating voltage. Now the upstream devices don't have to respond as frequently, and they're able to just do the average voltage regulation that they were intended to do. So this is a very common range that we achieve when we go on circuits. So 30 to 50% reduction in upstream tap changes on that device. And then finally, the install cost of approximately $200,000. That includes everything. So that's not just the STATCOM, but that's the pole structures as well. One of the other alternatives this utility looked at to resolve these issues was reconductoring, and that technique would have been over almost $2 million actually. And so we're seeing the STATCOM at 1/8 of the cost, much faster to install, and much easier to, from the standpoint of construction and installation, much easier, much faster project. And For this particular solar farm, a couple of other notes. So that solar plant was in a lagging power factor mode already. So there was already some configurations to try to mitigate some of these issues. Those were inadequate and insufficient. So the utility had to end up installing the STATCOM to fully mitigate all of these issues. And then another point here is that typically our modeling ability matched very closely with what happened in reality, and that's very common. Just a side point there: all the major distribution planning software packages now have STATCOM models in them. So SIM's got a great model. Synergy 6.8 now has a great model, and 6.7 I think is when they started that. MillSoft's got a good model, and then those are kind of the major packages, at least in North America. So basically, these doing these studies very quickly, just like you would use other apparatus in a planning tool to look at the impact, is now a very feasible tool to be able to size these STATCOMs for voltage regulation applications. So that was really the case study I wanted to share. And that really concludes the Tech Talk for today. So, Paul, I was thinking we can kick it over to you now.
Yeah. So, I like this concept of called hosting. You call the utility host, and you're hosting renewable customers, right? Is what you're doing. Customers that are putting PV, for instance, on the system. So when you think about a utility system, you get the central distribution substation, then it feeds radial distribution lines throughout that. And as you get more and more miles from the substation, that utility really can't be a very good host, right, to those renewable developers. So it's an interesting concept that you use the word host there, because they're being asked to increase their green energy production, but at the same time, they may not be able to host that green energy production without the VVO, right? Is what you're saying.
Or certainly if they had to get to the levels that they're trying to get to, and again, these utilities are challenging themselves now to get to 100%. But we're seeing 2045, 2040 even. So to get there, things have to be happening today, and there's a lot that has to come on the grid in order to get there. So having a tool that is very fast, that allows that build out to happen at the right time, at the right place, because it's apparatus, you can build it like that, as opposed to wire-based upgrades, which they take forever. You tend to overbuild first, and utilities have to kind of overspend in that situation. So this is a much more precise and granular investment in that sense as well.
Yeah, so it's very, very interesting, very interesting component that AMSC has developed, and I think it does address that renewable energy push that we currently are seeing, and also the power quality concerns associated with them. So Dave, I think what we're going to do, we're going to pop over to a question screen. I remind all the viewers, we already got some questions. I'm going to have Dave just review the questions real quickly, and then we're going to come back to you. For those who can't stay because we went a little bit long, that PDH certificate code is 888. So we're just going to go with 888 for that. Please, in fact, better yet, let's go VVO. We're going to go VVO for the
awesome.
Code. Yeah, that's to remember, so people remember VVO. So VVO is the PDH certificate code for today. We'll come back to you in about 30 seconds after Dave has had a chance to review the questions. All right, Dave, we have quite a few questions, and I'm just going to read them to you. You please answer to each question. So a question from Jeff. He's asking wood well motors, and I'm assuming maybe irrigation, residential, or even maybe oil and gas wells. But I think the answer or the question applies to all three. Would it correct for voltage flicker at the end of these lines, distribution lines?
Right. Yeah. So that's, I assume, Jeff, that you're referring to like the large inrush that an induction machine presents to the grid. So that's typically 5 to 7 times the rating of the motor during a starting condition, and that's a great application for a STATCOM because that's all reactive current during that inrush, and a STATCOM being a reactive current source is really a nice way to compensate that. So you would want to locate a STATCOM on the feeder near that well. It wouldn't have to be right at the well. It could be within about a half mile, typically, is what we guide, and it should clean those problems right up. Just to mention, yeah, Paul, maybe you want to mention that we had that other tech talk specifically on motor starting.
That's right, Tech Talk number 29. We have Dave was on prior to this one, and he had talked about motor starting applications with the VVO STATCOM. So that's another good one to go to, and he actually gets into more of the basics of what this D-VAR VVO system is. So next question is from Shabhanker, and he's kind of got a two-part question. Does AMSC provide the step-up transformer? And then if yes, then what are the special requirements of that transformer, being that there might be harmonics and other issues related to the STATCOM?
Oh, okay, yeah. So that's specifically when this solution is used in 25 kV or 35 kV distribution systems. That's when that external step-up transformer is required. There's really no special requirements. So that transformer that we showed in the picture, that utility actually used that transformer as a standard in their system. The nameplate rating of that was 1.25 MVA. So we were, in that installation, we're 1 MVA continuous. So the transformer was upsized a little bit, which is no problem. But we do not, for example, we do not require a special K-rated transformer, as an example, to deal with higher harmonics, because the STATCOM is making very high fidelity waveforms. So the THD from the STATCOM itself is very low, well below 2% on most feeder applications. So hopefully that addressed the question there. Yeah, I think it was, do we also supply it? So in that case, the utility supplies it, and these are standard utility transformers is what we try to be compatible with, or what we are compatible with. So utilities are buying those in volume, and utilities buy transformers in volume, period. So it makes a lot more sense for the utility to purchase those transformers typically for these sites.
Okay, so basically an off-the-shelf transformer almost is what you're
saying.
It
is. Yep.
Yep. So does AMSC provide any protective equipment like fuses or circuit breakers to protect the STATCOM, or is this something that the customer must supply?
Yeah, so all of those installations, actually all of our installations have been just protected with fuse. So fusing is the short circuit protection. We do generally recommend using current limiting fuses. Really, the industry is going towards current limiting fuses with all of the concerns about wildfire mitigation anyway. So kind of a good thing to do there. We do specify the parts that we recommend or equivalent part numbers from vendors of fuses. And again, utilities buy fuses, in huge volumes, and it makes more sense for the utility to source those than it does for us. The disconnect switch that's on the shunt branch of the VVO, that is supplied with the D-VAR VVO solution. So when we ship from our factory, we do ship it with those disconnect switches. And those disconnect switches are only there to basically our controller will trip or close that switch depending on the mode that it's in. So if there's a commissioning, it's going to be tripped, for example, or if there is a need to take it out of service, we're going to trip that switch. Otherwise, that disconnect switch is always closed during normal operation. And that switch is just a standard vacuum type switch that's broadly used in the distribution system.
Okay. Another question, and get those questions in soon because we're just about finished. How is the VVO coordinated with power plant controllers, and especially if we have to install the VVO far from the PPC and power plants with two connections to the grid? And I will get back to the other question. I forgot there was a question: is it available in three-phase or single phase? How do you supply it? So there's two questions. I passed one there.
Yeah. So on the topic of solar plant integration, often there is a impact study done and then a solution study done specifically for integrating let's take the case of like a 4 or 5 megawatt solar plant coming on. And as part of that study of the solution, we will look at issues like, does it make sense to have the STATCOM communicating with the plant controller, for example. What a lot of our utility customers are doing is the utilities that are really getting a lot of proliferation of distributed generation. So not just, let's say 1 or 2 plants coming in, but literally hundreds of megawatts. The power plants are actually being operated in a constant power factor mode. With typically some lagging power factor, so maybe 0.98, 0.97 lagging. That's a very easy setting to require of the developer. It's hard to mess that up. It's very straightforward setting to implement. And then the utility actually is using the D-VAR VVO in the volt-VAR mode to be managing and controlling that dynamic voltage. So with the plant in a fixed power factor mode and the D-VAR VVO in a volt-VAR mode, that's a very effective, cost-effective, robust way where the utility gets to continue to do what really in the distribution system, what they're really good at doing, which is controlling the voltage in volt-VAR mode. And then the plant just simply has to connect at the recommended power factor. So that's a pretty robust way to go. A lot of utilities like it, and I think we're seeing basically a lot more of that. In our deep dive on the solar application, we'll get into more depth on how to make those settings and what that looks like in terms of actual feeder implementation. I should just note though that basically the other question that comes up there is who pays for it, and so it is possible to have the D-VAR VVO be offered as an upgrade, just like utilities do with many other upgrades when a plant connects into the system. So a very common upgrade is like a recloser. When a large plant comes into a distribution system, an existing distribution system, it's very common that the upstream recloser has to be upgraded. The utility will own that recloser. The developer will pay for it. And so the very same concept can apply to the D-VAR VVO. So as part of that initial upgrade fee and upgrade program on the utility side, the developer can actually pay the utility up front, and then the utility then transfers ownership of the STATCOM and owns it, operates it for the next 20 years or 25 years on that circuit to continue to manage the voltage. So, hopefully that gave you some insight on that. And as I mentioned, we'll go into that again in a future Tech Talk.
3-phase and single phase, are they available in both forms?
They are, yeah. So each, that 3-phase installation is literally just 3 single-phase inverters that are each rated at 333 kVAR. So installing the D-VAR VVO on a single pole is no problem, or installing it on a single-phase lateral is no problem.
And I dropped 2 questions. Sorry, Christian, I passed your questions. One is, what is the switching frequency of the IGBTs? and it doesn't look like there's any filtering. You've already commented that it doesn't need much filtering, but you can comment
Yep.
on the frequency. And then one other question from Christian was, depending upon the operation mode, do you need CTs?
Yeah, so we do choose to keep that information proprietary on switching frequency. There certainly is a switching frequency, and we do comply with IEEE 519 harmonic requirements with a fair amount of margin, actually. So our harmonics are quite low. The current harmonics that are actually produced by the STATCOM inverter itself are quite low. I think, sorry, what was the next question, Paul?
So we're on our last question from Mansour. He's asking, does it need any maintenance? Is there failure rates available, mean time between failures, and available for the VVO?
Yeah, so we can certainly share that data with you in a follow-up. We do have MTBF information based on actual field performance. I think a couple of the key concepts, and sorry if they're a little repetitive, but one thing to know is that the MTBF does not depend on the number of fluctuations that the device is having, so that's a big advantage. And then asset planners at our utility customers do account for it as a 20-year asset life. So that's standard practice. And within that 20-year asset life, certainly there may need to be some service to one of the power electronic units, for example, but there is no routine maintenance required. So other than just inspecting the equipment, like is typically done for overhead equipment anyway, just making sure, visually everything's looking good, there literally is no regular routine maintenance requirement at all.
Okay, so get your questions in. We're just about done. I'm going to go to a rules of thumbs, do's and don'ts slide, and Dave, you're welcome to jump in whenever you like to add to what I'm saying here. And I made this up this morning in response to looking at your presentation outline. The do's and don'ts, and so specify the AMSC D-VAR VVO system to correct power quality, voltage disturbances, issues associated with fluctuating loads, and distributed generation facilities. We all heard the news this morning. Biden vowed to drop our carbon footprint by 50% by 2030. That's a pretty ambitious thing that he's vowed to do. That's going to require distributed generation. So remember, as you're injecting real power and reactive power into the network, you're creating voltage fluctuation. Much of our distribution systems are weak. The distribution lines are long. 13.8 kV is not that high of a voltage, so it doesn't take a whole lot of current or injection, whether it's real power or reactive power, to push that voltage around. So the VVO can help stabilize the system as we increase the distributed generation penetration into our networks. The D-VAR VVO increases the number of available sites for distributed generation. You have a utility out there, they're looking to install renewable generation within that distribution feeder. Right now, without the VVO system, the system being relatively weak, we have a limited number of choices. If you consider using the D-VAR VVO system, you extend the range by which you can install distributed generation. It increases the number of possibilities. To the load or to a distributed generation facility, a feeder with a D-VAR VVO system appears and performs as a stiffer line. So if you put a D-VAR VVO system on a line, it will appear to be a stiffer line. It's the same thing as reconductoring, and Dave went through that in the presentation. So that's an interesting concept. Avoid the cost of reconductoring, install the D-VAR VVO system. It's easier, much easier to do. Think about the D-VAR VVO system when you have a voltage flicker issue. The wells, soil mills, any type of pump stations, distributed generation facilities. D-VAR VVO can correct for flicker. Capacitor banks and voltage regulators cannot. They are slow devices. And then finally, we're on to the DOTE side. Don't stay with the mindset of using voltage regulators on feeders. that are connected to distributed generation sites. So you get the mindset, hey, I got the correct voltage, I'm going to use a voltage regulator. The voltage regulators can be subjected to over-operation and premature failure or require more frequent maintenance. This is especially true where you have solar as a distributed generation site. Each and every time the cloud passes over, the voltage regulator will look to maintain voltage and you'll get a switching operation, so you get premature failure. The D-VAR VVO system is faster to respond, has low operating costs, and requires no maintenance. And then finally, you can contact Dave Oteman. I got his email there. Just send him an email. He'll get you in contact with the right people to help you out. And one last thing, this was posted yesterday. It's in Power Magazine. And if you go to the LinkedIn invite, you can see the link to a white paper on the VVO system. And Dave's presentation actually followed along with this document quite well. So you might want to take a look at that. So Dave, we'll come back to you and we'll check for questions. There are no questions. We'll go to, why don't we go back to my presentation real quick and we'll just talk about next week. We are Tech Talk 48 next week, April 29th, 2 p.m. We have Cummins coming on and we're going to continue our discussion on hydrogen and hydrogen electrolysis. And we're going to have Michel Archambault from Cummins on with us next week to talk about electrolysis and electrolysis plants. Dave, we appreciate you coming on, and thank you for your time.
And thanks for having me, Paul.
Yes. All right. We'll see you.